Welcome to our journey into the fascinating world of light and mirrors. Light, as you may know, travels in a straight line, a property called rectilinear propagation. This simple fact leads to many of the amazing phenomena we see around us, from shadows to reflections. The speed of light is incredibly fast, about 3x 10^8 meters per second. When light hits a shiny surface like a mirror or water, it bounces back. This is called reflection. There are two important laws of reflection. First, the incident ray, reflected ray, and the normal all lie in the same plane. Second, the angle of incidence equals the angle of reflection. These rules help us predict how light will behave when it meets different surfaces. Let's explore how mirrors use these principles to form images and why understanding them is so important in our daily lives. Now let's dive deeper into spherical mirrors, which are mirrors shaped like a part of a hollow sphere. There are two main types: concave mirrors, which curve inward, and convex mirrors, which bulge outward. Each has a center of curvature, a principal axis, a pole, and a focal point. The distance from the pole to the focus is called the focal length. Understanding these terms is crucial for drawing ray diagrams, which show how light rays reflect and form images. For example, a ray parallel to the principal axis passes through the focus after reflection in a concave mirror. Meanwhile, convex mirrors always form virtual diminished images, making them perfect for vehicle rearview mirrors. These diagrams help us predict where and what kind of image will form real or virtual, magnified or diminished. Let's see how these concepts come together in practical uses. Moving forward, let's talk about refraction and lenses. Refraction is the bending of light as it passes from one transparent medium to another, like air to water. This bending is governed by Snell's law and the refractive index, which measures how much light bends. Lenses made of transparent material with curved surfaces use refraction to focus or spread light. Convex lenses are thicker in the middle and converge light rays, while concave lenses are thinner in the center and diverge light. Each lens has its own principal axis, optical center, and focal points. The power of a lens, measured in diopters, tells us how strongly it converges or diverges light. Lenses are everywhere, from cameras and microscopes to eyeglasses and telescopes. Understanding how they work helps us appreciate the technology all around us. Wrap up, let's focus on the essential formulas and real-world applications of what we've learned. The mirror formula and lens formula help us calculate image positions and sizes, while magnification tells us how much bigger or smaller an image is compared to the object. Remember, the sign conventions are crucial. For mirrors, object distances are always positive, but focal lengths can be positive or negative depending on the mirror type. Lenses also have positive or negative power based on whether they converge or diverge light. These concepts aren't just theoretical, they're used in designing headlights, rearview mirrors, cameras, and even solar furnaces. By mastering these basics, you're unlocking the secrets behind many everyday technologies. Keep exploring and you'll see the science of light everywhere you look.